So the paper I'm presenting is joint work with Lian Chen, who is at Oxford, and Jesus Gonzalo, who comes quite frequently to this meeting, who is at my former university in Madrid, Carlos III. So I'm going to talk about quantile factor models as a sort of logical extension of quantile regressions in the framework of high-dimensional data, where we want to extract factors for a big data set. Okay, so let me just start from scratch by walking you through the standard concept of an approximate factor model as a way of summarizing the covariance structure of a large panel data. So we have a XIT. Does this work? How is it? Where is the button with the star? Huh?
It's the button with the star.
Ah, I see. I'm used to the center. Okay, so we have a panel data with index by cross-section of n units and individuals and a time series of t observations, and we have the standard, Chamberlain-Rothschild structure, where we have R loadings and R factors, okay, one for each individual. The factors are common for all individuals. And then we have an idiosyncratic term. So the idea is that the variance-covariance matrix of the x's can be summarized by a smaller factor structure plus some idiosyncratic term, which could be subject to some cross-sectional correlation, etc., etc. So if the f's were to be known, then of course, and the expectation of the f, given the f's were equal to 0, this could be interpreted as a conditional approximate factor model. Okay? So this means that we focus on the mean to extract all these factors. So as is well known, factors and loadings would be extracted by minimizing a certain criterion function, which could be the Euclidean one. And then, for instance, for given f, we will just run OLS regression of the x's on the f's to retrieve the loading. So this is the standard approximate factor model. So where do we want to go? We want to go as from the conditional mean regression to the quantile conditional regression to a representation where you have that the XITs, the XITs is a function which depends on some stochastic variable which is uniformly distributed, just to capture all the quantiles in the segment 0, 1, times the factors. So in this representation, the factors again are common to all the units, but the loadings change according to this random variable. So of course, to have a quantile factor representation, we must have that for a given value of the uniform distribution, for a given tau, for a given probability, this must be increasing in the taus, because of course it's a cumulative distribution. So as we increase the horizontal aces, the mass of probability must be increasing. So this is important. This is increasing for all of t. And then you immediately see that if we define the probability of XIT being smaller than a particular value of tau in the interval 0, 1, then this is immediately yields the quantile. So the probability of the uniform being less than tau is of course tau. So the conditional quantile of XIT for given ft will have the standard representation. You immediately see also, of course, this is straightforward, that if we take the deviation of the stochastic representation, it's called the Skohorov representation of the quantile of the loadings process minus the loadings for a given tau, then you have like an approximate factor model where the quantile of the idiosyncratic component, the conditional quantile, is of course 0. So this is just straightforward. So this is the representation on which we are going to work. Let me just, in order to shed some light on what sort of models can be captured by that representation, let me walk you through different examples which will help you to fix attention. So the first one is a simple location model, a location model where you have just one factor, say, and you have error terms which are homoscedastic, so they are IID. Then if we represent the epsilon as the inverse of the corresponding probability masses, then we can write epsilon IT as the quantile of epsilon for the stochastic variable u, and therefore we have a representation in the form that I gave you before, lambda prime UIT FIT, where the loadings, the corresponding loadings, now have two elements. One is, of course, the corresponding quantile of the error term, and then you have the slopes here, and the factors. If you try to write this expression in this form, will have a vector of unities, will have an intercept plus the factor. So this is no other than the well-known result that you have a location model with homoscedastic errors, then a quantile representation will have quantile variation in the intercept but not in the slope. The second one is a location scale model. We restrict the sign of the factors, so just to fulfill the monotonicity criterion for the quantiles. So the idea here is that the same factor affects the mean and affects the variance. So there is a heteroscedastic model where the variation in the conditional variance given by Ft. So if we write again this we invert epsilon and express it as a quantile for a given value of the uniform distribution, this has a representation where now the loadings, lambda IT, have this form, and there is a single, as opposed here, where you had an intercept plus a factor, there is a single factor. So in this particular case, what we will see is that, as is well known also from heteroscedastic models, the quantile regression will have variation in the slopes rather than in the intercepts. Third, suppose that you have a location scale model where Ft has unrestricted sign, is the same model as before, location shift scale model. Then, as before, we can write it in this form, but now, of course, if Ft has unrestricted sign, when Ft is positive, the quantile is going to be this form, whereas the quantiles for the corresponding values of F when they are negative are going to have the complementary form. So that means that this type of model cannot be captured according to the representation I gave you before. A very interesting case is also a location scale with different factors. So you have Ft here affecting, and Gt, which is a different factor affecting the variance. Then again, by inverting epsilon t and writing it as a quantile of the corresponding choice of the uniform distribution UIT, you can see that now lambda IT corresponds to two factors, which both, the first one will not have quantile variation, whereas the second one is going to have quantile variation, right? You can also have models where the epsilon is not additive, the idiosyncratic component is nonlinear. Then, assuming some constraints on the sign of the FTs to make it monotonic, these models also have representations as the one I told you before. So it is the models are slightly more the representation is more general than the standard location shift models. So let me talk about the estimators. So, of course, trying to extract loadings at this moment and possibly factors at each quantile of the distribution of the xit, the most natural framework would be to get directly to the check function, which is the minimizing criteria for this function, and then try to find the values by linear programming of f. Here the big problem is, of course, f is a generated regressor, it's not known, okay, as opposed to the standard approach in quantile regressions, and lambdas. Okay, so this is, I put here question marks to point out that this is a rather difficult problem, as will come out later on. Remember, the check function is a function which gives asymmetric weights to the absolute values of the elements you are trying to minimize. So this is the check function. So it could be for the median, it would be just the standard absolute value function, and for the other ones you give more or less weight, depending whether you have positive or negative. So if you want to avoid, as a first stage, this problem, you could always note that using this representation, you can always write lambda I as the expectation for all the values of the uniform distribution between 0 and 1, and then express these as an error term, as an idiosyncratic error term, where now, of course, lambda is the mean, it doesn't have quantile variation. So this is like a conditional mean approximate factor model, and therefore, from this conditional mean approximate factor model, you could estimate the FTs by principal components or any other procedure, and then for given f, for conditional on estimated f, estimate the loadings for each of the quantiles. This representation, of course, is subject to stricter conditions, stricter assumptions than the ones used in the standard approximate factor model. Why? Because remember, the u's have to be independent of the f's. Okay? So this means that when you write the variance covariance decomposition, the matrix of the idiosyncratic components is diagonal. So we are back like in the old Chamberlain Rothschild representation. But unlike the bi-ng type of setup where you allow for cross-sectional and even sometimes series correlations. So this is this representation implies stronger conditions than the standard one. So from here, the natural procedure, as I said, would be just to take principal components for the factors and then just run quantile regressions for each individual, conditioning on the estimated factors. And you have to take that into account in order to derive tests, for instance, of whether these quantiles are the same across all quantiles, or for a particular quantiles, the loadings are the same, et cetera, et cetera. So the challenge here is, of course, the generated nature of this distribution. So basically, you need a little bit stronger assumptions that the standard ones used to draw asymptotic inference for these models. Remember, whenever you have a factor model, you have a rotation problem. The product of lambda times f can be split into lambda, some non-invertible matrix, its inverse, and the factors. So you identify up to a matrix, up to a rotation matrix. So the first result, which is one of uniform consistency, is that if you do this two-stage procedure, you get uniform consistency up to a matrix, which is this rotation matrix, which is you will later on identify imposing restrictions, like in the structural VAR models. You have so many unknown parameters that you fix by imposing some properties of the factors of the loadings. When NT when you have double asymptotics, you have these results, so you get this uniform consistency. So the issue is under which condition. Yeah.
May I ask you something on the previous?
Oh, please feel free to interrupt whenever.
No, so, but here, do you need something like the number of observations for each quantile estimate to get?
Yeah. Oh, yeah. I'm sorry.
So just so you need something stricter than in the standard model, because here you get a lot of lambdas.
You will see the conditions now in a moment. So basically, you can get asymptotic distributions for these loading factors. And the key result here is that you need this divergence condition to hold. This divergence condition is stricter than the ones which have been derived for standard linear factor augmented models. But remember, you must have n growing slightly faster than the square root of t, or even in nonlinear factor augmented regressions. So, for instance, you may have, as I said, nonlinear, where you impose some factors, nonlinear functions of the factors. Here it's by an NG 2008, t to the power 5 over 8. Here what we need is t to the power 5 over 4. So slightly larger n, okay, for given. So the intuition is obvious. I have this generated regressor, so I need somewhat larger sizes to estimate them. So basically, what you will have, this is the standard scaling factor in quantile regressions, and what you have is that this converges weakly to a vector of Brownian breaches, as in the standard papers by an NG. To estimate the scaling factor, then you need to choose a bandwidth parameter, which has to satisfy certain conditions, and we discuss them in the paper. So overall, we can renormalize the loadings just to draw some inference on them. For instance, we may be interested on a particular set of quantiles have the same loadings, etc., or all the quantiles have constant loadings, etc. So just to give you an example of how this asymptotic theory works, for instance, this is a location shift model, where a location scale shift model with the same factor. So we generated the factors with an exponential just to ensure that the non-crossing condition holds. And we estimated, we did some Monte Carlo. So this is a model, remember, where you will have a single factor, okay, because it's appearing in both. You don't have the intercept among the factors, and here you have the red PDF is the asymptotic normal distribution, and here you have for just in the paper there are many more for a combination of n 1000 t 100 the corresponding histograms. You can see that for the lower and upper quantiles, 0.75 or 0.25, there seems to be some small deviation, whereas for the central quantiles, it does better. Yeah.
So, one question. In a simple case, right, where I would have one common factor in the variance.
Yeah,
right?
in the variance.
In the variance, just in the variance. It's the only common factor. Now I can do the first stage, right?
Yeah.
But that first stage will essentially always tell me I have no factors.
Yeah, that's the issue I'm going to run in a moment. I'm just walking you through the way we took this issue.
But how do you take the assumptions then?
Later on I'm going to test, because this procedure is much easier than the other one. The other one will mean that I have to do everything in one stage. I have to estimate the loadings and the factor. That will come in a second, in a few slides. Okay, so the asymptotic distribution for the two stage, the advantage of the, let me just anticipate, for the one step procedure where we estimate the loadings and the factor at each quantile jointly, the problem is that we can get consistency but because of the accumulation of the generated regression problem and the non-differentiability of the check function, we can prove consistency but not asymptotic distribution. So that's why we went through this much simpler case where we can draw asymptotic inference. So later on we'll provide some tests of whether we are in this case or in the other case. Yeah, but obviously, if for instance, in the case where you have factors affecting the variance which are different from those affecting the mean, you are not going to capture all these factors by principal components. Yes, sorry.
So I also had a related question. So the number of factors here is known in the simulation? The number of factors is known?
The number of factors, yes, is known in the simulation. In some of the simulations, we will estimate them. But here there is just one factor, and we impose that in the simulation. We don't use a criterion just to estimate the number of factors.
Okay, so then the practitioner, how does he determine the number of factors?
Yeah, but although I'm showing you here the case where we assume known the number of factors, when you use some of the standard criterion functions, by an AG or an ASCII, etc., you don't get very far from there. You tend to choose one for this particular example.
I see. So then the binding would be okay.
Yeah.
Spring, even though the assumption.
If you have more factors, it may be more difficult to distinguish between 4 and 5 than between 1 and 2. I mean, here the trick is that we just simulated the data for one factor. Okay, so for instance, here you have the factor loadings. These are the true factor loadings, and these are the estimated factor loadings. So remember, for each individual, the quantiles are over T, over each sample size. So think of countries and growth rates of GDP per capita, or whatever other macro measure, or returns over time, or whatever. That's the way we do it. Okay, so to do inference, we can take several hypotheses. The first one, for instance, is that the loadings are the same for are known at the value z at any given tau. Okay, so for instance, suppose you give me a tau 0.25 or whatever, and then I want to test whether all the loadings for all the units in there are exactly the same at this 0.25. Or they may be totally constant for all tau. Or for instance, they may be equal, but then of course the loadings may be equal. It falls into what's so-called Durbin problem because you don't know the value of under the null. So for instance, being equal, it means that I can choose one of the quantiles of the loadings at a given quantile, say the median, and test whether this value is the same across all other quantiles. Okay, so you can except for this problem, basically with the asymptotic theory we just derived, you can run this test and use well-known distributions to test for them. For Darwin's problem, remember, the problem is, of course, that when you derive the asymptotic distribution of the test, you have an extra term, which is given to the fact that you are testing for whether a distribution is equal to a given distribution, one of whose parameters is not known. Okay, in this case, the median factor, the quantile at factor 0.45. So there is a trick to purge this non-centrality parameter, non-free distribution, which is called Camalache transformation, which is what we use just to purge this non-distribution free estimator. So let me go back to Gert's comment. So consider the example 4, the location shift model, where now you have factors G which are different from F. Okay? And assume that everything is mutually independent, as we assume here. Then, of course, immediately you see, and I won't spend, given the shortage of time, too much time, that if we apply our two-stage procedure, then we are going to capture F, but not G, right? So But G maybe contain important information, for instance, information about the tails or information on some particular parts of the distribution, which are useful for factor-augmented quantile regressions. Okay, so ignoring those elements may entail a significant loss in forecasting for these particular parts of the distribution. So we go back to the standard problem and then try to see how we could estimate lambda and f jointly using the check function. So we propose an iterative procedure, which is the most natural one, where you start for a given set of factors, and then you start iterating. So for a given set of factors, now we use the quantile regression of the excess on the factors and estimate the loadings, okay? Then given the loadings, we estimate the factors, and so on and so forth, until the process converges. This is the procedure where we call a one-step procedure. This is going to give, as opposed to the previous case, is going to give you FTs which depend on tau. Okay, so you are going to have different factors at different quantiles, not just different loadings, different factors as well. So let me give you just a simple example to see what you can get and what you cannot get from the two-stage procedure as opposed to the one-stage procedure. So let's assume I have this location shift, location scale model. Again, we generate GT with an exponential, and we run for this simulated series. We run the two-stage and then the quantile regression, the iterative procedure, until it converges. And then in this table, for different different combinations of n and t, and for 3 different quantiles, remember there are going to be as many factors as the factors are going to differ by quantile. I give you the R square of the factors estimated by principal components, okay, which is FPC, estimated by the quantile regression using the check function, and then something which we also discussed, which is the smooth quantile regression, which is just where you smooth out the kink in the check function by a given kernel, okay? So this is like a smooth quantile regression, and this is the quantile regression. So let's look what happened here. Not surprisingly, when you correlate the factor estimated by the two-stage here with the true factor, so this is a correlation of the true factor that of course we know, with the estimated factor by principal components, the correlation is high because it's capturing, the Fe is in the mean, so it's capturing it well. When you look at G, which is the one appearing in the variance, what you see is the quantile regression. Sorry, here, the principal component doesn't capture it at all. You see a very low R square, yes, not surprisingly either. When you look at the quantile regression, okay, it is both using the kink version and the smooth out version, what you see is basically it captures very well the mean, it captures very well the one in the variance, except at the quantile 0.5, and the reason is, of course, that we have assumed a symmetric distribution. So the quantile at 0.5 is 0. Okay, so you don't identify, here you get like a 0 there. So you don't identify the GT. So that's the reason why you get a hole here. But otherwise, the factor using the quantile and using the smooth out quantile capture very well. So this is telling you that if you have this sort of location scale model, then you have to go through the one-stage procedure. But remember, in the one-stage procedure, the price you pay, you know, we show that it is consistent, but we haven't been able to show was an asymptotic distribution. So for instance, comparing with the two-stage procedure, in this example where you have the same factor, so things work reasonably well here, what you can see is that the loadings in both procedures are basically identical, and the standard deviations of the loadings are more or less the same using the first stage and the second stage procedure. Let me just briefly summarize the problems in addressing this type of object. So the difficulty is, of course, the non-smoothness of the object function, and the fact for one factor you have n plus t incidental parameters, because you have the factor, n t observations, plus the loadings for the n individuals. So there are related studies, for instance, Ivan Fernandez-Val and Martin Weidner have a similar problem with n plus t incidental parameters, but they have a smooth rather than kinked criterion function. For instance, there are other studies which have non-smooth but only n incidental parameters. And remember, n plus t is just for one factor. If you have r factors, the dimensionality grows unboundedly. And so on and so forth. For instance, Cato and Galvao, in a recent paper, they smooth the check function, but they only have n incidental parameters. So the problem of incidental parameters in this case is really large. So that's why we want to know whether we can, there are circumstances in which the two-stage procedure, which is much easier and whose asymptotic distribution is known, can be used. Let me just take a small detour to talk about, so far, remember, what we have is the quantiles for each individual, for each country, for each region, for each asset. So the quantiles over time, so the growth rates, the low ones, the large ones, the middle ones, and so on. But suppose that we were interested in the cross-sectional quantiles. So at a given moment in time, let's look at the cross-sectional distribution and try to see whether we can model the conditional quantiles in there. So suppose we have this model, the standard location scale model, and assume that as opposed to before, assume that the alphas, that the loadings are stochastic, they have a mean and a variance and correlated with the idiosyncratic components. Then we can, again, as before, define the corresponding quantile, the probability that a particular observation is smaller than a given value. In this case, by assuming normality, this will be the CDF. And then we can define the corresponding quantiles. What's the problem here? The problem here is, as you can see immediately from the expression of the corresponding quantiles, it's not possible to estimate consistently the space span by F and G. They come together. So this means that the cross-sectional quantiles don't fall into the scope of this representation that we propose here. So let me just finish with a few empirical applications to give you a flavor. So for instance, this is just monthly US common stock returns from 1980 to 2014. Here,
You still have a lot of time, so it's not very...
well, I thought we were finishing at...
No, we're finished at 10:20.
Oh, okay. Yeah, okay, so okay, I got it wrong. I thought it was... Yeah. This is applying the two-step procedure to this big data set of common stock returns. So, of course, with the two-stage procedure, the best we could do is get some quantile variation at the mean and at the slope, at the intercepts and at the slope. If there are intercepts at the slope quantile variation, that would be a signal that the model is one where you have location scale with the same factors applying there. If we just get the variation at the intercept, this is just a signal that it's a pure location model. So, of course, it may be that there are factors in the variance which are different from the factors in the mean, and then we will not be able to capture them. Okay, so this is restrictive in the sense that we are ignoring this last part, although later on we'll test for that. So when you look at the factor loadings, well, you see that the intercept is clearly changing. It's increasing. Remember, it's a monotonic function, whereas the slopes are basically flat. Okay, don't change by quantile. So in principle, that would be consistent with a pure location model. When you look at the mutual funds returns, again from 2000 2014, you get again see this variation in the intercept, a little bit of variation because we could test using the previous results I told you about the constancy or non-constancy of these quantiles, but basically the message would be pretty much the same. Here we are using one of the Onatsky criterion to set up the number of common factors, so we are not imposing them. Of course, we don't know. This is an empirical data set. Then we have the Fama-French portfolios, and here, nicely, the number of factors chosen by the information criteria is 3, okay, as is well known. And again, the intercept seem to have quantile variation, but the other 2 factors seem to be pretty constant, right? So in principle, using this two-stage procedure, one would say, well, it's merely a location model, so whatever you get with principal components is fine. You can use factor augmented, and that will give you as much information as you could extract from the data. However, given the asymptotic theory that we drew before from the two-stage procedure, we can test, as I said before, whether these lines that I showed you before are constant across quantiles or have some slope, some monotonic transformation of them. For that, we have to use this Camalache transformation. And here you have, for different critical values, the number of units returns in each of the 3 data sets which don't reject the null of being constant. So basically, for instance, for common, at 5%, for instance, about 20% of the loadings that I showed you before reject the null of being totally flat over quantiles. So it's interesting, and this is what we are doing now, is identifying which are these stocks which have this quantile variation. For the funds, it's again, at 1% is still 11%, at 5% is still like 16% that reject the null. And for the Fama-French portfolios, it's basically 90% that don't reject the null. So to check whether the two-stage procedure is a good approximation, remember we are ignoring the fact that there could be factors affecting the variance. One, we take a sort of very simple approach, which is the following. We estimate the factors by principal components, and we estimate the factors with a one-stage procedure, with estimating factors and loadings all together through either the smooth or the original check function. So the idea is that if the two-step procedure works, it captures the true location shift representation of the model, then we know from the location shift model the extra factor that we would get that will not be achieved by principal components is an intercept. It's a vector of ones. Okay? So one thing you could do is estimate the principal components, estimate the factors by the one-stage procedure and regress it on a vector of ones and see if the R squared is close to 1 for each tau. Because remember, you have a factor for each tau. The other procedure, it would be, well, if there is a location scale model behind it, and the factors are the same, you have ft in the variance and ft in the mean, then of course regressing the factors estimated at different taus on the factors estimated by principal components should give you basically the same information. So that's the basic idea of deriving these R squares and confidence intervals for them to see whether they they fit into, if you reject that these R squares are high, then you are neither in the case of a pure location model nor in the case of a location scale model with the same factors, right, rather than different ones. So this is just a Monte Carlo, an R square, a Monte Carlo of a factor. It's a model where you have a pure location representation, and basically the first one, the red line, is the R square, where you estimate the R square between an intercept, a constant term, and the estimated factor by principal components. So basically you see that these always are equal to 1. And the other one is where you estimate the factors by the two-step procedure, by the principal components, and then together with the estimated by the one-step procedure. Okay. Here, because the distribution that we use is again centered at 0, you get a whole. This is just a finite sample problem that you get in a neighborhood of 0.5. This collapse in the R square, but this is basically the problem we were seeing before. And for larger sample sizes, this becomes just a spike at 0. So when you do these model checks for the 3 data sets I was telling you before, what you find is the following. This is the left is the stock returns, this is the mutual funds, and this is the pharma friends portfolio. So remember, this should be clearly close to unity. In both of these cases, we cannot reject that it's different from unity. But in this case, this is clearly different from unity. So this is clearly a case in the stock returns where there are some factors affecting the variance which are not affecting the mean. However, with respect to these, to the blue lines, which is regressing the one-step factors for each quantile on the common factors estimated by principal components, what you see is that for this case and this case, you cannot reject the null, that the R square is equal to 1, that they span in the same factor, whereas for this case you can. So basically, in the 3 cases, as in the test I showed you before, there are instances of subset of assets where there seems to be quantiles which differ by the position in the distribution. Okay, so that's a signal that there should be an effort to search for this specific variation in the quantiles. There may be something which affects the low part of the distribution, which is different from what affects the high part of the distribution, and the response is completely different. So well, the future research agenda, sorry, I rushed up a little bit, but I think the message is well conveyed, is, well, we are working now on forecasting exercises where we show that especially when you try to do stream quantile forecasting exercise, VARs, etc., value at risk, etc., identifying these quantiles, these factors which are affecting the upper or the lower part of the distribution changes the forecast the forecast power quite a lot. And I think that this is the most challenging task. Remember, so far there hasn't been any way, and we are not aware in the literature of results that can show this asymptotic distribution for the one stage. We managed to get a consistency result, but that is still a little bit unsatisfactory. So I think I'll stop here, and if there are more questions, I'll address them.
Any questions?
Yeah, please.
I guess the answer is yes, but let me ask, is it possible to cook some kind of diagnostic that tells us how much variability each quantile factor explains? Because of course we want to know how many are there, but we would like to know the magnitude.
Yeah.
If you find big magnitude.
Well, remember, we can test the size of the lambdas, the size of the loadings, okay? For given factors, for all factors, whether they are the same. So using that, of course, you can compute it. Yeah.
To show this consistency result for the general estimator, then you need there that these factors are pervasive, like in every quantile.
Yes,
In the
yeah.
a relevant
Yeah.
quantile.
Yeah, in the relevant quantile, yes, you need that. Yeah. You need to be more.
Okay.
Yeah.
Okay, yeah, so Juan knows I like this paper a lot. So what I was thinking is, since here the quantile variation is in the temporal dimension,
Yeah.
can you discriminate it with other type of time variation in the loadings? So for example, you could have just like a autoregressive evolution in the loadings, which would still allow you to estimate the principal component, by principal components, the factors, and then you could do common filter to extract the loadings.
That could be a possibility. I mean, at this stage, we want to just take the model as it is, rather than do approximations. But
Yeah, just to understand what it is that drives time variation, whether it is the quantiles or whether it is something else.
no, here is obviously the quantile.
Yeah, no, sure. Let's say empirical.
So when you're doing tests for all values of tau,
Yeah.
are you under the case of multiple testing, or
Yes,
so you got to correct the p-value?
yes, yes. Bruce?
For forecast intervals, the conditional quantiles are exactly the output we want. This is probably an underappreciated fact. So, in other words, if you want to do a forecast interval, you can go directly to what you're doing, just pick off the quantiles for a fan chart with different quantiles. So it's a really beautiful method of making fan charts.
Yeah. Yeah.
It could be.
Could be, yes. That's, yeah. I agree.
I have a question. Can you give us an idea about the computational cost of the method? Like how much time does it take to estimate to get the results for, say, the Flamand French data set?
It's not not so intensive. I remember, I mean, at this stage, instead of estimating the factors for the continuum, we are just choosing a particular quantile, so we are restricting it to particular quantiles, like a grid of 0.1, 0.2, 0.3, etc. That minimizes the cost. Okay, so because you do the check function, not in general, but for a particular subset of weights. But I think for the Fama French, it took like 2 days of, just to get it converging.
Okay, well, let's thank you.